Good afternoon, everyone. Thank you for attending my presentation. So today I'll be presenting our research titled Transforming Construction Robotic Education with Virtual Reality, Analyzing Student Presence and Self-Efficacy. So the project was conducted in collaboration with Zhang, my advisor Professor Houtan, Jebelli, and myself Amit Ojha uh, from Department of Civil and Environmental Engineering at University of Illinois Urbana-Champaign. To begin, let's consider the growing role of robotics in construction. Globally, over 81% of the construction firms anticipate adopting robotic technologies in the next 2 decades. And the trend is driven by advances in autonomous equipments, 3D printing, and robotic arms, among others. Recent studies suggest that nearly half of all the construction tasks could be automated in the near future. This includes functions like bricklaying, material transport, and inspection. But while the technological shift is clear, the challenge lies in preparing the future workforce, especially the students and early career engineers, to engage with these systems meaningfully and safely. Unfortunately, there are two significant barriers to successful robotic integration on the construction sites. Uh, Workers often feel uncomfortable or unsafe operating around the robots, and also there is a lack of structured training on how robotic systems function and how to collaborate with them in dynamic environments. So these challenges underscore the need for an updated educational approach, one that not only imparts knowledge but also builds confidence and practical readiness. Currently, construction engineering and management curricula, however, still rely heavily on passive learning strategies that are lectures, slides, and textbook readings. While these methods are important for foundational knowledge, they are limited in their ability to simulate real world complexity, particularly for the topics like human robot collaboration. So, students often complete these modules without ever experiencing the spatial constraints, task coordination challenge, or interface interaction involved in robot assisted construction work. And this gap between theory and practical practice is where immersive technologies such as VR offer transformative potential. So, virtual reality VR offers a unique ability to create task oriented interactive simulations where students can learn by doing. Unlike traditional methods, VR can model construction site with realistic robots, constraints, and hazards. It enables experiential learning. Students can explore, interact, and troubleshoot tasks as they would in the field, but in a safe and controlled setting. Studies have shown that such immersive environment improve knowledge retention, confidence, and situational awareness, all of which are crucial in construction robotics education. So, in this study, we focus on two psychological constructs that play a pivotal role on student learning effectiveness. So, one is sense of presence. So, this refers to the feeling of being in the virtual world. A strong sense of presence enhances realism, engagement, and thereby the learning outcome. Similarly, another psychological construct is self-efficacy. So, this is a learner's belief in their ability to complete tasks and solve problems. High self-efficacy correlates with better learning outcomes, persistent and transparent through the real-world performance. So our research seeks to measure how a VR-based learning system influences these two outcomes in a construction robotics education. So to frame our work, the problem statement is that traditional lectures often have difficulties instilling pragmatic skills in construction engineering students due to the inability to eliminate the complexity within human-robot collaborative construction environment. And our research objective is to develop VR-based models for teaching construction robotics to CM students and assess their effectiveness in terms of self-presence and self-efficacy. So, to assess the VR-based learning of construction robotics safety in terms of student presence and self-efficacy, so this study follows two-step methodology. So, in first step, we develop modules for immersive learning of construction robotic safety. We developed 3 modules, specifically robot exploration, modules related to robot application, and modules related to robot implementation. And the next step of our methodology, we evaluate the sense of presence and self-efficacy using questionnaires. So we developed a multi-module immersive training platform in Unity, accessible via VR headset. So we developed three learning modules. So the first modules introduce students to common robotic system in construction such as concrete printers, bricklaying robots, and aerial drones. Module 2 emphasized the practical application of these robots in construction, focusing on the robot placement and operational planning. And Module 3 emphasized the task-oriented control, where the students can perform the simulation involving direct robotic manipulation and coordination. Each module was built on the last to create a cohesive understanding of robot capabilities, task sequencing, and real-world constraints. So in the next step of our methodology, which was the inference of the developed system on sense of presence and self-efficacy. After we developed those modules, we conducted a control study with 40 construction engineering students who participated in the full VR training. So after completing the modules, students responded to two validated survey. So first survey that was measured, leveraged was a 44 item questionnaire, presence questionnaire that measured 4 key dimensions: spatial presence, ecological validity, engagement, and negative effects. So there was 44 items which measured these 4 dimensions, and the students were asked to rate those questionnaires on a 5-point Likert scale. Likewise, to assess the self-efficacy, we leveraged an 8-item new General Self-Efficacy Scale, which is used for measuring student confidence in completing tasks and achieving goals. So this was an 8-item questionnaire where the students also rate it on a 5-point Likert scale. So this was the result for our assessment of sense of presence in the developed virtual environment. So the VR environment received high scores in spatial presence, suggesting that students feel realistically immersed in the construction site scenario. And the ecological validity, you can see the mean of 4.1 is also high, indicating that experience was perceived as relevant and reflective of real-world conditions. So importantly, the negative effects of scale related to disorientation or discomfort scored low. The mean score was 2, which supports the usability of the system for extended educational deployment. And these findings confirm that the immersive environment successfully created a realistic and comfortable setting for learning. In terms of self-efficacy, students reported significantly increase in confidence after completing the VR modules. Many indicated that they feel more capable of understanding robotic function, collaborating with robots in constant environments, and making informed decisions about robotic deployment in construction. So this boost in self-efficacy is crucial because it implies that the VR-based learning not only informs students but also empowers them to take initiative and engage with the technology in the field. Together, these findings demonstrate that the VR-based instruction is an effective tool for enhancing engagement and realism, improving confidence, and offering an accessible alternative to resource-intensive robotic training. Now, to summarize, this study evaluated the effectiveness of VR as a teaching tool in enhancing student presence and self-efficacy within the HRC education in the construction sector. The findings demonstrate that the virtual environment provides a robust sense of presence, particularly in spatial presence and ecological validity. The high self-efficacy scores indicate that the environment supports students' confidence in their ability to achieve goals and tackle challenges related to construction tasks. Of course, there are limitations to note. The study was conducted with a relatively sample size, and the study did not include the physical robot interaction, which could enhance the realism of certain coordination. So for future research direction, future studies could include a much larger and more diverse group of participants to enhance the reliability of results. And also, we can perform the longitudinal tracking and field scale validation. So lastly, I want to acknowledge all my colleagues at RaiseLab and all the funding agency Without their support, this research wouldn't have been possible. Thank you.